Hi there. This video is going to introduce differential equations. I'll start by explaining what a differential equation is. Of course, most equations you've solved in the past, you've been solving to try to find a number. In a differential equation, you're solving to try to find a function. Here's an example. This differential equation asks us to find a function y of x with the property that its derivative, dy by dx, is its square plus 3x. So we can form differential equations using combinations of the function y, its derivatives, x, adding them together, applying functions. So here's another example. This differential equation asks us to find a function y of x with the property that when we multiply it by its own second derivative, we get the function sine x. So if these equations seem scary, and sometimes they are in fact scary, it's worth remembering that there's one family of examples that we understand very well already. This is a family of examples which look like dy by dx equal to some function of x. And to take a fully explicit example, I could choose f to be cos, for example. So we'd be looking at the differential equation dy by dx equals cos x. This asks us to find a function y of x whose derivative is cos x. But that's the same as asking for the indefinite integral of cos. We're looking for a function that differentiates to cos, and that's the same as asking for the indefinite integral of cos. So we can solve this by integrating both sides, and we get that y is equal to indefinite integral of cos x, which is equal to sine x, plus, of course, a constant. Now, this feature is very, very common in differential equations. We found not one solution, y equals sine x, but a whole family of solutions. Y could be sine x, or sine x plus 3, or sine x minus 7, or sine x plus any constant we like. We'll see that again and again. Differential equations tend not to have one solution, one function of x, but a whole family of them. Note, this differential equation was quite simple to solve because we understood it was just asking for the integral of the right-hand side. That's quite rare, but this is a trick that's useful again and again in solving differential equations. We find something clever, or maybe we transform it into some form that looks like this, and then we can integrate. This doesn't solve them all, but it solves a good few. To see why it's useful to have words to describe differential equations, it might be worth thinking back to when you were at school and learning how to solve other sorts of equations. There you learnt the words linear and quadratic, so you knew what a linear equation was and what a quadratic equation was. And it was worth having these words because you knew that you had techniques for solving some equations, and you could recognise them when there were quadratic equations, for example, and you knew how to solve quadratic equations. So what are the words we'll be using here? The first words I want to tell you about are partial and ordinary. So a partial differential equation is one that involves partial derivatives, such as the partial derivative with respect to x or the partial derivative with respect to y. An ordinary differential equation, on the other hand, is one that only involves the ordinary derivative d by dx. So, for example, an example of a partial differential equation might be partial a by partial x is equal to y partial a by partial y squared minus y. Ordinary differential equations are the ones we've seen in the last couple of videos, and examples of those might include dy by dx squared equals y plus d squared y by dx squared. Partial differential equations are, in general, much more complicated than ordinary differential equations, and you'll be pleased to learn as a result there are no partial differential equations in this course. We'll focus entirely on ordinary differential equations for the rest of it. Okay, onwards for more words. Now I'm going to tell you about the order of a differential equation. So the order is the order of the highest derivative that occurs. So, for example, if we have the differential equation d to the 7y by dx 7 equals d squared y by dx squared minus y cubed. This is an order 7 equation. It's a differential equation of order 7 because there's a 7th derivative in there. To give another example, if we have the differential equation y d squared y by dx squared equals x to the 8y, this is an order 2 differential equation because the highest derivative that occurs in there is a second derivative. So, most of the derivatives you've seen so far, arising in real life that is, are first and second derivatives. Similarly, most differential equations that arise in nature are of first or second order. That's not always true, however. For example, there's a partial differential equation that describes the motion of waves in shallow water, and that's a third order differential equation. Mostly, for the rest of this course, we'll see first and second order differential equations. The next thing I want to tell you about is the difference between a linear and a non-linear differential equation. So a linear differential equation consists of derivatives of y multiplied by functions of x as all its terms. So an example of a linear equation would be sine xy plus cos x dy by dx equals 0. So each of the terms here, each of the terms consists of y, or one of its derivatives, multiplied by a function of x. And that's a linear differential equation. For another example of a linear differential equation, maybe we could have 3 d squared y by dx squared plus e to the x dy by dx equals 7y. Every term in this equation consists of y, or one of its derivatives, multiplied by a function of x, and then we add and subtract all these terms. A nonlinear equation, on the other hand, features things which aren't just functions of x multiplied by y, or one of its derivatives. So an example of a nonlinear equation would be d squared y by dx squared cubed equals 7y. So this is nonlinear because this term here isn't a derivative of y multiplied by a function of x, it's a derivative of y cubed. Similarly, another example of a nonlinear equation is e to the xy dy by dx equals 3x. This term is linear, but this term isn't. We don't have a derivative of y times a function of x, we have a derivative of y times a function of x and y. So this equation is non-linear. In general, linear equations are much easier to solve than non-linear equations. We won't be focusing our attention entirely on linear equations, but most of the time we will, particularly later in the course. So I think that's enough words to be getting on with for now. So we talked about partial and ordinary, we talked about the order of a differential equation, and we talked about whether it's linear or non-linear. We'll be using those later to explain which ones we can and can't solve by various methods.